In this lesson we're going to look at pH and the strength of acids and alkalis. We remember that the pH of a solution is a measure of the concentration of hydrogen ions or hydroxide ions in that solution. Now the concentration is really the number of ions in a given volume, per unit volume. And we represent that in chemistry with this phrase here with little square brackets. So this symbol here means the concentration of hydrogen ions, and this symbol here means the concentration of hydroxide ions. Last lesson we looked at indicator charts, and we remember that the indicator chart tells us the value of the pH. So in the middle of the chart we have solutions with a pH of 7. That means that the concentration of hydrogen ions or hydroxide ions is 0. That's to say there are no excess hydrogen or hydroxide ions in the solution. Now as we move this way the pH increases from 8, in fact up to 14, and going the other way it decreases from 6 and down to 1. So as we move this way the concentration of hydroxide ions increases, and as we move this way the concentration of hydrogen ions increases. That's to say the number of hydrogen ions within a unit volume increases that way, or the number of hydroxide ions in a given volume increases as we move this way. So what actually affects the pH of a solution, or the concentration of these ions? Now the first factor is really the type of acid or alkali. It depends upon the nature of the substance. So let's compare some different acids and alkalis. Remember that when we add carbon dioxide to water, when we bubble carbon dioxide through water, we produce carbonic acid. Okay, just writing an equation for that, so you have CO2 plus H2O produces H2, and this is the formula for carbonic acid, CO3. Now when carbon dioxide bubbles through the water, some of it dissolves but not all of it, and the resulting acid is quite a weak acid. Now that means that carbonic acid produces a small concentration of hydrogen ions. Okay, so we can write a low concentration. Okay, so we can represent those hydrogen ions in the acid, okay, with these little red dots. So you can imagine symbolically that represents a low concentration of hydrogen ions. Now if we take another gas like sulfur dioxide, well, we find that sulfur dioxide, when you bubble that through water, that's a lot more soluble, much more soluble than carbon dioxide, so nearly all of this gas dissolves. Now when this happens, the sulfur dioxide reacts with water to produce a stronger acid called sulfurous acid. Sulfur dioxide. You can watch both of these experiments if you go to the Watch and Learn section in acids and alkalis. That produces sulfurous acid. And we can write the formula, so we have SO2 plus H2O, and the formula for sulfurous acid is H2SO3. There we go. Now this acid, sulfurous acid, is a lot more capable of producing hydrogen ions than carbonic acid. So we can say again that sulfurous acid produces hydrogen ions but a much larger concentration. So if we look at this diagram we can see that the acidic solution produced by dissolving sulfur dioxide in water, producing sulfurous acid, results in a higher concentration of hydrogen ions, a much higher concentration than carbonic acid. That's to say there are more hydrogen ions in this beaker per unit volume, so we would expect that the pH resulting from carbonic acid would be, around about pH 5 to 6, whereas the pH resulting from sulfurous acid, and you can see this in the experiment in the Watch and Learn section, the sulfurous acid will turn indicator paper sort of this kind of dark pinkish colour, so you'd expect the pH to be around about 2 to 3 for sulfurous acid. Now likewise, the pH of an alkaline solution depends on the type of alkali that's added to the solution. So for example, in this case we have sodium bicarbonate. Now sodium bicarbonate is also known as baking powder. Okay, so you can find this in your kitchen. So when you add sodium bicarbonate to water, and you can try this in your kitchen, for example, you'll find that it is only partially soluble. So even after some stirring, there will still remain some bicarbonate at the bottom of the beaker or glass. Now when baking powder dissolves in water, it produces a weak solution of sodium hydroxide. You can put your hand in it and you can feel that it's quite soapy, because sodium hydroxide is the same substance that you find in soap. So this results in a low concentration of hydroxide ions. As with the acids, we'll represent the hydroxide ions with little purple dots. This represents a low concentration of hydroxide ions. Now if we take another substance such as sodium hydroxide, now that's also known as caustic soda, and if you add a small measure of that to water, well, it will completely dissolve in the water very easily, unlike the sodium bicarbonate. And as a result of that, it produces a high concentration of hydroxide ions. We can represent the formation of these ions using an equation. So we can write NaOH, that's sodium hydroxide, produces sodium ions, okay, and the AQ means that the sodium ions are in solution, plus OH minus. And likewise we can represent the hydroxide ions in this solution. You can see there's a much higher concentration than with the sodium bicarbonate. So if we were to measure the pH of each solution, we would find that the pH of the bicarbonate solution will be typically around about 8 to 9, whereas the pH of the sodium hydroxide solution would be typically around about pH 12 or higher, since there is a much higher concentration of hydroxide ions.